Welcome to the Java Multithreading, Concurrency, and Performance Optimization course, where you will learn to build fast and responsive multi-threaded applications. My name is Michael Pogrebinski, and I'll be your instructor for this course. I started my career as a computer architecture engineer at Intel. There, I first acquired the low-level programming skills and the passion for high-performance programming. For many years as a professional software developer, I've been building and architecting cutting-edge software solutions for healthcare, simulation, education, and augmented reality smart devices. Today, I'm a principal engineer and software architect at one of the biggest real-time ad exchanges in the world, located here at the Silicon Beach in Los Angeles, California. Nowadays, every PC, phone, or cloud server is equipped with multiple CPU cores and multi-threaded capabilities. Businesses are processing growing amounts of data every day, and the demand for engineers with skills in concurrency and performance is higher than ever. That's why I've designed this course to give you all the tools you need to become a successful and confident multi-threaded application developer. The course is focused on Java, but the majority of the concepts you will learn are directly applicable to any modern computer programming language. By the end of the course, you will be able to choose the right concurrency tool for the job, correctly architect your software, and build multi-threaded applications, web servers, algorithms, and libraries, all with performance and good user experience in mind. In this course, we will learn some operating systems fundamentals necessary for multi-threaded programming. We'll learn to use multiple threads, including some advanced techniques. We'll learn how to measure and optimize the performance of multi-threaded programs and algorithms, and we'll also cover practical real-life examples such as user-facing applications, image processing algorithms, web services, and many others. And to help you validate your progress, I've included many quizzes and assignments. This course is for students who want to master new practical skills without compromising on quality, but who do not have the time to enroll in long academic courses or boot camps. I've handpicked the topics that will give you the most value based on my many years of experience. So whether you're a professional software engineer, a student, or a hobbyist, this course is right for you. All you need is some basic knowledge in Java and the passion for programming. Feel free to look through the course description, and I look forward to seeing you inside. Hey guys, welcome to the first lecture. In this lecture, we'll first get the motivation and the intuition behind multithreading, and before we start writing any code, we'll have a short introduction to operating systems fundamentals. So first of all, let's understand why we even need multiple threads. The two main reasons we need threads for are responsiveness and performance. Let's explain these terms, starting with the responsiveness. We're all familiar with how frustrating it is waiting for hours on the line for customer service support. Sending a message to somebody and not hearing back from them for multiple days, or clicking on the purchase button in an app and not seeing any confirmation. Those are all examples of poor responsiveness, which we would like to avoid if we want our clients to like our product or our app. Suppose we have an online store web application that serves thousands of users. The application stores all the information about each user's purchases in a database. If one user makes a large purchase of multiple items, which results in a long operation in the database, and in the same time another user is desperate to complete his purchase, that second user will not get any response until the web app is done responding to the first request. With multithreading, we could actually serve multiple users simultaneously by serving each request on a different thread. We will learn how to do this with practical examples farther in the course. Responsiveness is particularly critical when it comes to applications with a user interface. A good example for that can be a movie player application. The application is showing us images, playing the audio, and in the same time we expect that if we move the mouse or click a button, we would get an instant feedback for our action on the screen. This kind of responsiveness can be achieved by using multiple threads, each thread for a different task, and it's generally very hard to achieve otherwise. By multitasking quickly between different threads, our computer can create an illusion that all those tasks are actually happening at the same time. The term we use for this kind of multitasking is concurrency. Notice that we don't even need multiple cores to achieve concurrency. Even with one core, we can create responsive applications by using multiple threads. The second reason we need multithreading is performance. As mentioned before, using concurrency, we can create an illusion of multiple tasks running in parallel just with a single core. With multiple cores, we can truly run multiple tasks completely in parallel. The performance impact of multithreading is the ability to complete a complex task in a fraction of the time it would take us to complete it otherwise. We can finish much more work in the same period of time than with a single thread. And if we're running a high-scale service on multiple machines, we will need less machines, which will also mean less expenses on infrastructure and more money in our pocket. So now that we have the motivation for multithreading, and we understand the parallelism and the concurrency concepts, which brings us the desired responsiveness and the performance, there is one caveat. Multi-threaded programming is fundamentally different than the traditional single-threaded sequential programming. And a lot of the intuition we have from single-threaded application development will actually break when we introduce multiple threads. But no worries, in this course we will lay the groundwork and we will learn all the tools necessary to become a successful and productive multi-threaded programming software developer, and you will be able to write highly performant and responsive applications. Now let's have a short introduction to operating systems fundamentals to put things in the right place and understand what threads actually are. When we turn on our computer, a special program called the operating system is loaded from the disk into the memory. The operating system takes over and provides an abstraction for us, the application developers, and helps us interact with the hardware and the CPU so we can focus on developing our apps. All our applications, such as the text editor, a web browser, or a music player, reside on a disk in the form of a file just like any other music file, image, or document. When the user runs an application, the operating system takes that program from the disk and creates an instance of that application in the memory. That instance is called a process and is also sometimes called a context of an application. Each process is completely isolated from any other process that runs on the system. A few of the things that the process contains are the metadata like the process ID, the files that the application opens for reading and writing, the code, which is the program instructions that are going to be executed on the CPU, the heap, which contains all the data our application needs, and finally at least one thread called the main thread. The thread contains two main things, the stack and the instruction pointer. In a multi-threaded application, each thread comes with its own stack and its own instruction pointer, but all the rest of the components in the process are shared by all threads. We will discuss these concepts more in detail later in the course, but in short, the stack is a region in memory where local variables are stored and functions are executed. And the instruction pointer is nothing more than a pointer that points to the address of the next instruction that the thread is going to execute. It's easy to understand why each thread has its own stack and its own instruction pointer if we remember that each thread is executing a different instruction in a different function at any given moment. So let's quickly summarize what we learned in this lecture. We got some motivation for why we want to have multiple threads in the first place. We learned the importance of responsiveness and how we can achieve it with concurrency using multiple threads, and high performance, which can be achieved by parallel execution. We later talked about what threads are and what they contain, such as the stack and the instruction pointer, and also what the threads share in a process, such as the files, the heap, and the code. See you in the next lecture.